we're presented here with a collection. It says, consider the set W, which consists of all those positive integers with this property. What is W? Well, that's quite a difficult question. This might be an infinite set, it might be finite set, it might be all of n, none of n, it could be a lot of things. So, but we have an advantage. We're working on the collection, under the collection of positive integers. What does that mean? That means that we have an initial point. We can start checking for things. And then from that point, maybe identify a pattern that we can exploit. So let's answer a few questions. The first one, well, is 1 in W. Well, there's only one way to test. We'll take this one, introduce it here, and then evaluate the truth or falsity of the statement inside. So what would be that? Well, suppose we have the sum from 1 up to 1 of the expression 2i minus 1. But what is this? Well, this is nothing else but only one term, meaning 2 times 1 is 1, which is 1. So while we have that 1 squared is 1. So the expression that we have here actually is equal to 1 squared. So what does that mean? That means that this is false. In other words, 1 is not in W. What if we place a similar question now with 2? It's 2 in W. Well, similarly, I have the sum ranging from 1 up to 2 of the expression 2i minus 1, which now results into a sum with 2 terms, namely 2 times 1 minus 1 plus 2 times 2 minus 1, which of course now becomes 1 plus 3, which indeed is 4, which is 2 squared. So once again, this is equal to that. So this sum is equal to the square of the number of terms that it has. So nope. 2 is not a member of W. One more level of experimentation. I'm going to say it's 3 in W. Well, same thing. I'll start the sum starting from 1 up to 3 of 2i minus 1. Well, that one results in basically the same expression that I have here, plus a third one, a third term, which is now this 2, 1, minus 1, plus 2 times 2, minus 1, plus 2 times 3, minus 1, which of course reduces to 1 plus 3 plus 5, which is 9, which is 3 squared. So once again, 3 fails to be a member of W. So now that's an indication. Look at the pattern that we're developing here. It seems like it doesn't matter which positive integer we select, it won't be in W. But then that becomes something of this form. Plain. For every n positive, n is not in W. Well, that's a perfect case for a proof by induction. But look, the base case is already covered. We did it here. So the only thing that is remaining is the inductive step. So what are we going to do? We're going to make the assumption. I'm sorry, not the assumption. I'm going to start with this. Let k be a positive integer and assume that k is not in W. What we're going to demonstrate is that k plus 1 is not in W as well. But what does this mean? Well, this means that the sum ranging from 1 up to n of the term 2i, okay, k, sorry, minus 1 is actually equal to k squared. I'm just negating the expression that I have here. Okay, so if I develop the sum that ranges from 1 up to k plus 1 of 2i minus 1, well, this one actually may be decomposed in two terms. One involving the sum from 1 up to k, and then the k plus 1th term. And what will be that? Well, that's simple. We just have to replace I with k plus 1, and we'll get the following. 2 times k plus 1 minus 1. And then, well, we'll explore this one a little bit more. But now we have the assumption that this is k squared. So I know that that is k squared. This one, we can just do some algebra, and we get that this is 2k plus 2 minus 1, which of course reduces to k squared plus 2k plus 1, which, well, we can easily identify this as a binomial squared, which is k plus 1 squared. So indeed, what this says is that this expression is actually k plus 1 squared. In other words, k plus 1 is not a member of W. Well, the claim is proven. Now this is a fact. What does that mean in terms of W? Well, there's nothing in W. W is the empty set. Take care.